We learned about Hooke's law, we learned about how, tension compression changes the shape. And now today we are going to look at stress and strain. So first of all, let's talk about stress. Now stress is basically defined as force applied per unit area. Okay. So the symbol of stress is like this. We make it more clear like this. And I mean, it could be made like this as well, so it's fine. Let's do it like this. Okay. And the stress is equal to force per unit area. So its SI units would be pascals or simply Newton per meter square. So it's just like pressure develops. Is it clear, Varisha?
Yeah.
Okay. Now, when you apply stress to something, okay, it also causes a strain in that particular object. Now, strain is simply a ratio of strain is simply ratio of extension. Oh, in fact, let's not write extension. Let's write change in length, right, x over the original length. So the symbol we use for strain is E, and E is basically change in length over original length, and because it is basically a ratio of similar quantities, so it has no units. Is it clear? So they can give you strain in both the ways. They can give you strain in this sort, or they can also give you in percentage. So if they have given you in percentage strain, then only the difference is that x upon L is going to be multiplied by 100%. Is it clear?
Yeah.
Now, so then comes basically Young's modulus that basically we're working for. Young's modulus is defined as the ratio of stress over strain. The symbol we use for Young modulus is capital E, right? And Young modulus is given by stress over strain. So generally, if you want to write it as, let's talk about the SI units first. So SI units are pascals, so that's the same. Because stress is pascals and strain has no unit, that's why. However, you can expand this too, because stress was force over area, and strain was change in length over original length. So basically, Young modulus then can be written as force over area, that's stress over strain, and when you simplify this, so this will be f times L over A times x. Is it clear, Arisha? Arisha? Okay, well, that's cool. I hope you understand everything, right, up till now?
Yep.
Okay, let's do a question then. So in a question, it says that, right, funny. Okay, part A. What is the compressive stress in each upper leg bone of a 7-ton elephant if the bone is vertical, cylinder with a diameter 25 centimeter and the elephant stands normally. Normally means perpendicular to it, okay? And then in part B, it says if the Young's modulus of elephant bone is 19 gigapascals and the bone are originally 95 centimeter long, how much would they reduce in length if the elephant stood up on its back legs, and what assumption do you need to make? Okay, Varisha, do you understand the questions? Varisha?
Yeah.
Okay, now can you try this? Give it a shot and then I'll explain it if you don't do it.
convert centimeter to meter, right?
Yes, of course. Varisha, are you tired from you've come from school?
No, I just woke up actually.
Okay, all right. Okay, then this question will wake you up even more.
Is it 81 Pascal?
The first question, it's the first part.
Yeah.
Okay, let's check then. So it is like 7 ton basically is 7,000 kg. 7,000 kg is the mass of the elephant, and it is basically the bone says it seemed to be a cylinder. So the area would be pi by 4 d square. You know how this formula for area comes, Varisha?
I didn't use this one.
You use pi r square?
Yeah.
Okay, that's fine. But basically it comes from like, because area is pi r square and r is diameter by 2. So you put it back in. So it would be d by 2 whole square. So it comes out to be pi by 4d square. So that's a faster way anyway. Okay. So stress would be 7,000 times 9.81 divided by pi by 4. This is 0.25. That's how you convert into meters square. So that would be
Oh, my bad. I multiplied 9.8 with 7 instead.
okay, then obviously that is going to be wrong. So pi times pi by 4 and multiply by 0.25 square. Oh, so Varisha, this is 1.4, 1, 2, 3, 4, 5, 6 times 10 raised to 6 pascals. That should be the answer. Okay, can you do the next one, please? Okay. Okay. Ariba, how are you?
Sir, I'm good. How are you?
I'm good too. Okay, Ariba, you are late. You just came.
Sir, I came around 4:15.
Okay. So you're doing the question as well?
No, sir, I was just doing it with you.
Okay, do the next
I
one.
will do this one. I will
Okay.
try this one.
Okay, please. Okay, in 10 minutes, you guys need to rejoin. Okay, done, you guys? This isn't that difficult.
One second.
So, okay, waiting.
Okay, I got 1.36 into 10 raised to minus 4.
1.36 into 10 raised to minus 4 change in length, right? Okay, let's try this then. That's in meters, you say?
Yeah.
Okay, let's see. So, Young's modulus is given by stress over strain. The stress we already found. Oh, by the way, if the elephant basically stands now in basically stands on four legs, and now it's like two legs, right? In fact, oh my god, basically, if the bone is vertical, oh my god, what is the compressive stress? Basically, there's a mistake in the previous chapter, a previous question as well. The mistake is that I didn't see that basically it's just that the basically the total mass of the elephant is this and total weight is this. So it says what is the compressive stress in each upper leg. So we have found, oh okay, we have to divide, I mean the weight will be divided by 4, right? Yep. So that's something wrong. So it means each leg will have, we have to divide by 4 actually, then it will be the correct answer, and then we can go further. I'm really sorry about that. 1.4 times 10 raised to power 6. I just realized this, and this is 33.5 times 10 raised to power 1, 2, 3, 4, 5 pascals. This should be in each leg. Okay, now what you're going to do is, because he says he stands on two legs, I read it somewhere, okay, the back legs. So if he stands on back legs, then we would say that the stress is going to be 3.5 times 10 raised to 5 times 2, because now there are two legs, each one has the stress, and the strain is what we need. The Young modulus is 19, giga is basically 10 raised to power 9. So Young modulus is gonna be something like 3.5 3.5 times 10 raised to power 5 multiplied by 2 divided by 19 times 10 raised to power 9. So it's going to be 0. Okay, let me do it the other way. 3.7 times 10 raised to power minus 5 as strain. Is it clear?
Okay.
Okay. Now this is the ratio, right? So then Young's modulus, strain is given by change in length over original length. So this is 3.7 times 10 raised to minus 5. The x is basically given by, this is what we need, and this is 95 centimeters. So let's multiply this. So that would cause it to have, wait a second please, something like 0.0035 centimeter. Let me check once more because I'm not sure entirely if this is correct. Wait, let me check it this way on the side. So let's try to, because he's standing on like 7 tons is his weight, and then mass, and then 9.81, that is the total mass. And that comes on 2 legs, which means the weight has to get halved for each leg, and that is the weight, and the force would be this, and the area is pi by 4, 0.25 whole square. So let me just try to find the stress first and see if it is the same that we've been calculating, because I think it should be different, but it's okay. Shift pi by 4 times 0.25 whole square, and now stress is somewhat like 7.0 times 1, 2, 3, 4, 5, 10 raised to power 5 pascals. Okay, all right, and then we have to use Young's modulus stress over strain. So strain is going to be stress divided by, and that should be 19 times 10 raised to power 9. So 7 into 10 raised to power 5 divided by 19 times 10 raised to power 9. Yeah, it's basically 37. It's the same thing. Okay, 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5. Yeah, that's the same. Fine. So we were on the right path anyway. It was minus 5. Okay. Now we got basically the strain as this much. So basically this will be the change in length. Okay, is it clear? Okay. All right. So now this is what you should be getting, this answer. Okay, whether you do it from the first method or second method, it's the same thing. Now, what would be the assumption that you might take here? Can you please tell? Yes, Varisha. What do you think the stress, the assumption that we might have to take here? Marisha. Marisha, can you please tell me what is the assumption we're going to take here?
I'm not sure.
Okay, but you do understand the question, right?
Yeah.
So basically, the assumption we take, basically, there are a couple of assumptions that you can write, but if I were you, I would write that we are assuming that both legs are perfect cylinders and the weight is equally divided between two. Do you understand? So otherwise one bone might, have a greater compressive strain because of course that it might be taking up a larger load than another one. Okay, now write this down please and let me know if something you need help in something. Okay, Varisha, is it clear?
Yeah, I'm good.
Okay. So Varisha, now the last thing we're gonna do is basically the graph of this before we basically close the class, really. So this is stress in pascals here, and this is strain right here. Whenever we're going to draw this graph, the graph will start from the origin and then it will show you something. Generally, it's like this. Okay, a graph shows this is sort of a general graph, right? Is it clear?
Yeah.
Now, when you just look at the graph, so just before it starts to bend, this is basically, let's say, point A. This is just after this, there is E, and just here there is, okay, let's write P, let's write Y, let's write M, and let's write B. Okay, so these are the points. Now I just want to tell you one by one what exactly this is. Okay, so this point P is the limit of proportionality. You already know this. So limit of proportionality is basically, you already know, it's a point beyond which Hooke's law is not obeyed. All right. Then comes this point E, and E is the elastic limit, which means point beyond which a material does not return to its original shape after unloading. Unloading means when the force is removed. Okay, you already know this now. The third thing is y, and y is basically the yield point. Now, yield point basically is a point beyond which the material undergoes a sudden increase in extension as its atomic structure is reorganized. All right. So, for slight increase in stress, it shows larger strain. Is it clear? Look at the graph. So it's not increasing that much as it was before, but now it's showing a lot of strain as well. Understood?
Yeah.
Okay. Now you might see this point M. M is basically called the ultimate tensile stress. If it's compressive, it would be called if it's compressive force, then it would be called ultimate compressive stress, but that's the same thing. Basically, this is the highest possible stress this material can take. Usually we write it as UTS like this, and if you look at it, this is the maximum stress that it can take. Understood?
Yeah.
And now the last point is B, and B is basically the breaking stress, and breaking stress is a point where the material fractures, so it just snaps. Okay, it breaks from the weakest point. That's how it's done. So you can write this down, Varisha, and then you've drawn the graph as well.
Yeah.
Okay. And then we just need to cover one small, say, topic. That's the experiment, and then that would be it actually from this chapter as well. So your unit 1 then will be finished. Okay.